Hello, in this video, I'm going to discuss the best case performance analysis of Quickshot. So, best case becomes when the input has balanced partitioning. As we know, Quicksort is going to have a pivot element, and that pivot element is going to partition the array into halves or subproblems. If this is the array, and if we take 5, so I'm trying to discuss with the help of example, and this is the input which will have balanced partitioning, and I will show that how this input is going to give order of n log n in best case. This is the input, and initially to apply Quickshot, I hope that you know how algorithm works, partitioning algorithm works here. Partitioning algorithm is the algorithm which is used by Quickshot algorithm in order to take the pivot element, whichever pivot element you are choosing, take that element to its correct position, or if you are taking 5 as pivot element, then its correct position will be at 4th place. Why 4th place? Because if this is not sorted, then after sorting, tell me where 5 is going to be. 5 is going to be at 4th place because firstly 2 will come, and then 3 will come, and then 4 will come. 2 will come first place, 3 will come at second place, and 4 will come at third place. So the correct position of 5 is at 4th place. So we have to bring this to its correct position. We don't know about rest of the elements, how they are going to be, but one thing we are fixed with is that the pivot element is going to be at its correct position after applying partitioning on it, partitioning algorithm on it. So this is the pivot element which is marked in the black circle, and then the algorithm says that you have 3 pointers initially. The first pointer is at 5 initially, which is known as pivot element. The second pointer is j pointer, which is at 0 index, and the third pointer is I pointer, which is at 1 lesser than j position, that is -1. I is -1, j is 0, and pivot element is 5. Now each time algorithm says that you have to compare the element at j position with the pivot element. If that element at j position is found to be smaller than pivot, then increment the pointer I value and exchange the values at I and j. But if the element which is being compared with pivot element, or the element at j index, is smaller than the pivot element, then we have to increment. But if it is greater than the pivot element, then we don't have to increment it, and then we'll be going to the another element j pointer, increment j pointer, then compare it with the pivot element. So algorithm says that when you find j element at j position to be smaller than pivot element, then increment I and exchange the values of I and j. But if the element at the j in position is greater than pivot element, then do nothing, just increment the value of j and compare the other element with the pivot element. This is the concept of partitioning algorithm, and finally in the loop we'll do this, and lastly when we reach n-1, then exchange I plus 1 value, whatever the value is at I plus 1 position and pivot position, you have to change that when we reach this part. So this is the algorithm of Quickshot. Now let's compare. 8 is compared with 5, 8 is greater, there will be no change, j will be incremented, I is at -1, j is at 1. 6 and 5 is compared, 6 is greater, no change, 7 is also greater, no change. Now 3 is smaller than 5, so increment the value of I and increment the value of I, and then we are going to exchange elements at I and j position. So I is at -1, incrementing I becomes at 0, I comes at 0 index. Now I is at 0 index and j is at this index which is pointing at 3. So we have to exchange these two values I and j. So 3 will take the place of 8, 8 will take the place of 3. This is how it is going to be 3, 6, 7, 8, 2, 5. Now again we have been comparing till this, we have compared till this part. Now 4 will be compared, again it is smaller, so again increment the value of I and then exchange the values of I and j. So I was here initially, I was at here, but we got this as smaller, so we incremented from -1 to 0. So now I is at 0. And then we have compared 4 again, we got smaller value than pivot. Then again increment. So if we increment it, I will come at the position of 6. So exchange the values 6 and 4. So here 4 and 6 has been exchanged. Now again 2 is a smaller than 2, smaller than 5. Now I was here, so increment the value of I will be here. Then exchange the position of 7 and 2. 2 and 7 is exchanged now. And as I said that if we reach n minus 1, if this is the size of the array is n and this is 1 lesser than n, so this position is n minus 1. When we reach n minus 1, we're gonna take this I plus 1 and exchange with the pivot. Okay, so we were at this position, I was this, I plus 1 will be at this, so exchange these two positions, 5 and 8. Now 5 has come to its correct position and it is the 4th place where it should be in the sorted list. So this is how this pivot element has partitioned the problem into two halves, and both of them has 3 elements in the left part also, in the right part also. Those two part is again going to be separated, again going to be solved separately, and again it will be partitioned, and again this part will also be partitioned. So this is the balanced partitioning, because we are having same elements at the both parts. And also what is going to be the time complexity is going to be n by 2. If we have elements, the total element is considered to be n, then this part is going to take n by 2 and this part is also going to take n by 2. So n by 2 and n by 2, and this n will add for the partitioning cost it is going to take the pivot element. When we take this pivot element to this position, then of course this is going to take some time, and this will be order of n. And not only this pivot element is going to take that time, other parts will also take, but when we are adding it, then it will be order of n, all of them. And if you solve it, it could be solved using, I think, it will be solved using Master's theorem, and you'll get this value order of n log n. So this is how we get the best case when the input is having balanced partitioning. When the input is random value, you'll get this balanced partitioning. So this is the best case time complexity of quicksort. I hope that it has helped you. Thank you very much.